In this video, we are going to understand the shape and size of orbitals. By shape of an orbital, we mean the shape of the region in space in which there is more than 90% probability of finding an electron. It is determined by the azimuthal quantum number L, while the orientation of the orbital depends on the magnetic quantum number m. The size of an orbital increases with the increase in the value of the principal quantum number n. Shapes of orbitals in various subshells are to be shown. Now, orbitals, let's say what it is, they are the imaginary place or imaginary 3D space where electrons exist, and an orbital can contain maximum 2 electrons. Now, people have different kinds of confusions regarding how do exactly orbitals look, and do the orbitals overlap with each other? Does the electron, which is of suppose the 2s electron and 2p electrons, is there any region where there is a common probability of finding them both? So let us visualize the shapes and sizes and orientations of each and every orbital, and let's see how do they exactly look. So this is the s orbital. This is non-directional. You can see there are 3 axes: the x-axis, y-axis and the z-axis. Now the s orbital is perfectly spherical. It's completely non-directional and there are no nodes. Absolutely, there is 0 nodes. Now let's check into p orbital. Now p orbital in general looks like this. Now this is the d orbital, which has the double dumbbell shape, while the p orbital has a single dumbbell shape. Now this is f orbital. It has a very complicated geometry. Now there are 3 types of p orbitals: px, py and pz. Now here we can see the px, py and pz all together in a single diagram. Now there are 5 types of d orbitals: dxy, dyz, dxz, dx square minus y square and dz square. Now this is dxy. Dxy is basically on the xy plane, but this is actually 3D. You can see along the z axis there is no probability of finding the electron. So this is dxy. The red colored rod shows the x axis, while the green colored rod is the y axis, and the blue colored rod is the z axis. So you can see this is dxy. Now we have dyz. This is along the yz plane, and along the x axis there is no electron probability. Now this is dxz. This is on the x and z plane, and along y axis there is no probability of finding the electron. Now this is dx square minus y square. Now the lobes are on the axis, on the x axis and the y axis. Along the z axis there is no probability of finding electron. This is not in the xy plane, but this is oriented along the x axis and along the y axis, as you can see. This green colored rod, you can see, is the y axis, and red colored rod is the x axis. So this is dx square minus y square. Now we have dz square. Now this has a very beautiful shape. There is a dumbbell shape along the z axis, and you can see a spherical kind of shape along the x and y axis. So this is the 3D diagram. Now let's see some examples. Now this is helium. There are 2 electrons in its only shell. There is 1s2. So in this diagrams we will be seeing how the different orbitals or the sub-energy levels look. So there is only 1s and only 2 electrons. Now here we have beryllium. Now this 2 electrons, the outermost shell electrons are shown in the diagram. You can see there is 1s as well as 2s. The 1s is the inner sphere and the 2s is the outer sphere. Now the 2s engulfs the 1s. Okay. Now in general the 2s electrons can be anywhere. The 2s electrons can be there in the place of 1s also, but they can be outside the place of 1s also. So 2s engulfs 1s. So you can see this 3D diagram very clearly. Now we have a bit more complicated thing. This is carbon. Electronic configuration 1s2, 2s2 and 2p2. Now see, you can see all the three orientations of p, px, py, pz, three are present. Okay, you are seeing that some region is overlapping. The p has some region in common with the 1s and some region in common with the 2s. This is the actual real life diagram, what it really looks like. The probability is everywhere. So in this region, in some regions like this, near the nucleus, you can find the 1s electron also, 2s electron also and 2p electron also. But in general, 2p electrons will be at a further distance. The average distance from nucleus of 2p electrons will be higher. Now this was carbon, and now let's check into oxygen. More complicated. Now let's check into neon. You see the 2p6, that means the p orbital, the p sublevel is completely full. All the px, py, pz, everything is full. Now only the outermost electrons are shown in the diagram. Now we have magnesium. You see, it's really very complicated. You can see 3s has come into place. So together all the orbitals look like this. Then we have argon, a bit more complicated. Now you see 3p has come into existence. 3p. Now 3p is engulfing 2p. 3p, it starts from the nucleus only, from near the nucleus, and extends more. So in general, 3p electrons will have more average distance from the nucleus and will have more energy thus. But the thing is that they can come together, they can come near each other. For example, a 3p electron can come near a 2p electron. Okay, they are all in a cloud and in a kind of 3D mixed kind of motion. Now we have calcium, a bit more complicated. We have 4s. You see, 4s is engulfing everything kind of. 4s is huge. Oh, now this comes really very complicated elements of the periodic table. Now let's just not discuss, let's just see how they really look. So it's getting more and more complicated. So we have 3D, it's really complicated. So this has helped you to understand more and more clearly about the orbitals and ships. Hope you will like this video. Thank you.